Hi everyone. In the next two lectures, I'll be discussing a little bit deeper into the time domain analysis of first order systems for varying inputs, for various inputs. Okay. Uh, Actually, I wanted to cover frequency domain analysis, but I felt a little bit of time domain analysis is still left out, so I'll be covering that in the coming two lectures. Okay. So let's consider a simple first order system with a time constant tau characterized by a first order differential equation given by this. Now, one of the most commonly applied inputs to a first order system is a step input. So, wherein you apply the step input, and we have seen in the last class, when you start from zero initial condition, the output tries to catch up to the input, and the output voltage is given by, here Vx is the step value, Vx into 1 minus e power minus t upon tau into u of t. Okay. Now, in this equation, one particular parameter of interest is, so eventually we say that the output reaches a steady state, the output reaches a steady state value. Now, what time does it take to reach the steady state value? Okay. And that parameter is of interest to characterize a first order system. So, a time constant tells you how fast does the system react. Okay. But it does not tell you when does the system actually reach the steady state value, the final value that the output is supposed to reach. So that parameter is what we call a settling time. Okay. It's denoted as Ts. It's the settling time. Now, to actually measure the settling time, what you need to do is that to find when V naught of t reaches its steady state value, which will be V of x, Vx. Now, for V naught of t to reach Vx, from this equation here, you have to substitute t equal to infinity. In that case, your V naught of t will be exactly equal to Vx. So, by that definition, your settling time will actually be infinity. But I can't use that as a definition. So, I can't use the definition when V naught reaches Vx, okay? Because that happens only at infinity, because we know that the output only asymptotically reaches the input. So, if I can't use that as a metric because that's not a finite value to compare. So, which means for any system with any time constant, the settling time is always infinity. Okay. So, if I use the time at which V naught reaches Vx as a metric, then it's infinity for all those systems. So, but rather then we'll start using a more practical way of defining settling time. So, instead of waiting till the output reaching Vx, we'll find a value when your output is very close to Vx. So, two of the most popular such way of measuring the settling time is this 95% settling and 99% settling. So, 95% settling is the time at which your V naught has reached 0.95 of its final value, or 95% of its final value, and this you can find by substituting it in the equation. The first order equation, the solution for a step response. From this you will find your Ts to be approximately 3 tau, 3 times the time constant. And similarly, for 99%, you can show that the settling time is 5 time constants. In fact, in 5 time constants, your output will reach 99.3%, but 99.32%, but it's approximated to 99%. So when you mention settling time, you also mention the percentage settling. Okay. So when you actually look at the output actually reaches at 3 time constants, it reaches 0.95 of Vx, and at 5 time constants, it reaches 99% of its final settled value. Also, you can very easily see from this equation that at 1 time constant it reaches approximately 63% or 0.63% or 0.63 of its final value. So, the other thing that you need to notice from these equations is that the settling time is proportional to the time constant, and which should sound pretty obvious, because time constant tells you how fast the system is raising. If your time constant is low, then it means your system is responding very quickly and your settling time will also be low. Okay. So that's all about settling time. So when you define settling time for first order systems, you also mention the percentage settling along with it. Okay. So now we will go about analyzing first order systems for different inputs. So three of the most commonly applied inputs in any first order system are an impulse, a step, and a ramp. Now in this analysis, throughout the analysis in this lecture, I'll assume the area under the impulse is 1. So such an impulse, it's called unit impulse, and it's written, the area is written alongside the impulse to denote its area, and the step value is assumed to be 1, and such function is called unit step function, and the slope of this ramp function is assumed to be 1, and that function is called unit ramp function, defined as t into u of t. The slope of this function is 1. Now first we'll analyze for an impulse input. Delta of t is an impulse. When I feed it to a first order system, I'll call it FOS as the first order system, what will be the output of this system? To solve this, I'll very quickly use a simple first order RC circuit, because it's very intuitive when you solve it using that. Assuming that the initial condition across the capacitor is 0, I've applied a sudden impulse at t equal to 0, okay, a unit impulse. Now at t equal to 0, when you apply an impulse, the first order system will see it like a very high frequency input, so your capacitor voltage cannot change instantaneously. So your capacitor voltage will remain constant, or it will stay at 0 initially. When your capacitor voltage at that instant stays at 0, the entire impulse voltage will drop across the resistor, and that will generate a current I given by 1 by R into delta of t. That's the impulse current that is set in the resistor. Now that current flows into the capacitor, and as soon as it flows into the capacitor voltage V naught of t is integral of the capacitor current, so it will be 1 by R delta of t dt. So the system is starting at 0 to t, I'll get 1 by tau, RC is tau, okay. So at 0 plus, suddenly the capacitor voltage will rise to 1 by tau. Now after that, the input to the resistor, the impulse function goes to 0 after that, so the input can be treated as 0. So you have a situation that I'll redraw the circuit like this. So the resistor, and you have stored a voltage of 1 by tau across the capacitor. Now this is again a simple discharging circuit. The resistor will discharge the capacitor until the potential difference between the two plates goes to 0. So by that, again it's a first order system, the initial condition is 1 by tau, the final value is 0, so it will just decay down like this. So when I feed an impulse to a first order system, the output of this system is 1 by tau e power minus t upon tau into u of t. Again, this expression can be very easily obtained when you use Laplace transforms. You will get the same expression using a Laplace transform analysis, okay. I'll leave it up to you to try that out. It's very, very simple. You can find it in any standard textbook, okay. So now we know impulse response. Now how to find step response? So the step function and impulse function are actually share a very interesting mathematical relation. In fact, a step function is an integral of an impulse function. So an impulse function exists at t equal to 0 and it's 0 afterwards. So when integrated in this region, the value of the integral is 0, and I keep on integrating, I keep increasing t. As t increases, I'm going to plot this function, which is an integral of integral of impulse. It is 0 here. At the moment it encounters an impulse, suddenly the area will increase, and suddenly you will see a step change of value 1. After that, the impulse function goes to 0. The impulse function is 0 here in this region, so there is nothing to integrate here. So your integrator will retain its previous value and it will stay at 1. So the integration of an impulse is actually a step function. So what I'll do is I'll first take an impulse and pass it through an integrator. This is a symbol for an integrator, and feed the integrated output to a first order system. And the output at this point will be a step response. Okay, the output at this point will be the step response. Now what I'll do is I'll use a very simple property from a theory of signals and systems, that if I have two systems with impulse response h1 of t and h2 of t, okay, and I feed an input x and get an output y, if I interchange the order of the systems and I first have h2 and h1, I'll still get the same output. Okay, so this is called commutative property. Using that, I'll just feed an impulse to a first order system first, so that will be your impulse response here. And then I'll integrate the impulse response to get the step response. Okay, so this will be your delta of t. First you feed an impulse to a first order system and then integrate the impulse response, you should get the step response. Now we know the impulse response of a first order system is 1 by tau e power minus t by tau into u of t. Now if I integrate this function from minus infinity to t, in fact minus infinity to 0, it integrates to nothing. So I'll start from 0 to t. The value of this function integration is simply 1 minus e power minus t upon tau. You can very easily show this integration. So this is your step response, and we already obtained this in the last lecture, and we get the same response by integrating the impulse response. Okay. Now next thing is to obtain the ramp response. Now to derive the ramp response, again I can first feed an impulse through an integrator. I'd get a step function. Now you should notice that the step function, the ramp function r of t, is actually an integral of step function, right? So when I have a function, let me just draw it here. So a ramp function, if I consider an interval t, the area under this, the integral is simply the area under this rectangle with the unit amplitude. So the function will just increase with increase linearly as you increase t. So the function is t into u of t. So a ramp function is actually an integral of step function. So this will be your ramp function. Then I feed this to a first order system, I'll get the ramp response for a ramp input. Now again I can change the order of the systems and then first feed an impulse to a first order system. You get your impulse response here, and then feed it to an integrator. You get your step response. And after that, feed it through an integrator, it get your ramp response. Okay. So all you need to do to get ramp response is you just have to integrate the step response. So the step response is 1 minus e power t upon tau into u of t. So if I integrate this from minus infinity to t, I should get the ramp response. Now the value of this integration, if the first term is nothing but t into u of t, minus the second term, it's nothing but integral e power minus t upon tau into u of t, starting from minus infinity to t. When we derive the impulse response, e power minus t upon t into 1 by tau is the impulse response. When you find the integral of that, you get the step response, which is 1 minus e power minus t by tau into u of t. So if I take tau to this side, I can write this part of the second part of the integral as tau into 1 minus e power minus t by tau into u of t. Okay. So this is your ramp response. This equation looks a little complicated, but it's very intuitive to understand it. So we'll actually try to interpret the results. So first I'll just plot the impulse response. So for an impulse response at t equal to 0, as soon as you apply an impulse, the equation we got was it starts at 1 by tau and eventually decays down to 0. And for a step response, it starts at t equal to 0 and eventually reaches the steady state value, which is 1. Okay, so this is 1 by tau e power minus t upon tau, 1 minus e power t upon tau. And for the ramp response, when you start at t equal to 0, to draw the ramp response, it's little bit mathematically involved, but let me just try to show that. Okay, so when you are actually plotting your step and impulse and step response, if you notice for a very large, when your t is much greater than the time constant, the output eventually tries to reach the steady state value. Okay, now how do you find the steady state value? You make t equals to infinity or t much greater than tau. When you make t much greater than tau, this value goes to 0. When you make t much greater than tau, here for a step response it goes to 1. Now what happens for a ramp response? So ramp response, we just showed the mathematical equation is t into u of t minus tau into 1 minus e power t upon tau into u of t. So when t tends to infinity, this term tends to 0. So the equation tends to t minus tau into u of t. Okay, this is nothing but a delayed ramp function. This is a delayed ramp function. So first I'll plot a ramp function and a delayed ramp function. A delayed ramp function is actually starting at t equal to tau, it is 0 here, and it will actually go like this. Okay, now this is your steady state value. Now we also discussed that a first order system tries to asymptotically reach the steady state value. So using that, it will start from 0, first order systems. Only for impulse it doesn't start from 0. For any other finite input, it starts from 0. Okay, and then eventually it asymptotically reaches this value. You can draw it like that, or you can mathematically draw this function. So using graphical analysis, you can solve it. First draw t into u of t, and then draw the function tau into 1 minus e power minus t upon tau. So this is this function, this part of it. Then subtract the two graphs. So when you subtract the two graphs, at t equal to 0, both of them are 0. So this is 0 here and this is also 0 here. You start at 0. Eventually we reach the function t minus tau. So eventually the function should reach t minus tau into u of t. So this is the response for a ramp input. And the interesting point to observe for a ramp input is that in the steady state, the ramp input reaches, as I said, t minus tau into u of t, and the input is actually t into u of t. So when you subtract the input from the steady state output, you get tau into u of t. Okay, so which means there is a steady state error of tau second of value tau between the input and the output. Okay, there is a constant error between the input and the output. So that's what you need to observe from this analysis. Okay, so the steady state error in a impulse input is 0, because input is 0, output also eventually goes to 0. For a ramp input, again the steady state error is 0. Okay, output also eventually catches up with the input, the steady state error goes to 0. But for a step input, but for a ramp input, if you see, it runs as a parallel line compared to the input. So there will always be some finite error between the input and output. So I'll stop at this point. In the next lecture, I'll go a little bit detailed in more detail about the responses to different inputs.